हेलो स्टूडेंट्स। तो वही हम अपना टॉपिक कंटिन्यू करेंगे, मैटर इन आवर सराउंडिंग्स। तो फर्स्ट उसका टॉपिक था, चैप्टर मैटर इन आवर सराउंडिंग्स का फर्स्ट टॉपिक था फिजिकल नेचर ऑफ मैटर। तो आज ये टॉपिक को फिनिश करते हैं। लेट्स स्टार्ट। ओके, तो टॉपिक वही पहला टॉपिक कवर होगा। ओके, व्हाट इज़ द नेचर ऑफ मैटर। तो आप देख सकते हो यहाँ पे मैटर तीन फेजेस में है। दिस इज़ द सिनेरियो ऑफ अ बीच। यू हैव मैटर इन योर लिक्विड फेस। ठीक है, यहाँ पे लिक्विड फेस में ये लिक्विड है। ठीक है, फिर यहाँ पे सॉलिड है। दीज बिल्डिंग्स, दीज ट्रीज, दे आर सॉलिड। फिर आपका गैस, दिस एयर, एटमॉस्फेयर, दिस इज इन गैसियस फेस। तो दीज आर द थ्री स्टेट्स ऑफ मैटर दैट यू एक्सपीरियंस इन एवरीडे लाइफ। फिर आपका आई हैड टोल्ड लास्ट क्लास दैट मैटर इज मेड अप ऑफ एटम्स। आपके केस में एटम्स, मॉलिक्यूल्स, and rarely it is made up of ions. Okay, so this atmosphere is made up of N2, O2, CO2 and so many other gas molecules. Water आपका H2O, इस पे salt होगा तो NaCl। फिर organic matter जैसे तो सब dissolved होते हैं, तो lots of salts are dissolved. This is your particulate. So matter is made up of particles. So particulate nature of matter. फिर आपका जो बिल्डिंग्स हो गया, इट इज़ मेड ऑफ कैल्शियम ऑक्साइड। में कैल्शियम ऑक्साइड इज़ अ पार्ट ऑफ सीमेंट। फिर आपका सेल्यूलोस, ट्री का बार्क, ट्रीज़ में आपको सेल्यूलोस मिलेगा। दीज मॉलिक्यूल्स मेकअप योर मैक्रो वॉट एवर यू सी, दीज आर मेड अप ऑफ दिस माइक्रो substances. That is why matter is said to be particulate. It is not continuous. Okay, you don't get one big piece of air. Air is not a big piece of a single air large envelope that is covering our entire planet surface. These are small molecules that have coalesced, like not coalesced, they have aggregated together to form a macro bulk substance which you can feel. Air you can't see, but you can feel and sense it. Okay, we'll go to the next slide. Solids, liquids and gases, they are the fundamental three states of matter. These days actually two more they are already developed, established. One is plasma, I told you last class. Next is Bose-Einstein condensate, BEC, or Bose-Einstein condensate. Okay, so these are two states of matter that we do not experience in our everyday lives, because these plasma exist at very high temperatures. Okay, if you have a plasma TV, you can sort of see effects of the plasma state of matter. Plasma exists at very high temperature. BEC exists at very low temperatures, close to reaching about minus 273 degrees Celsius or 0 Kelvin. Okay, plasma is very high temperature. Plasma is found in stars. Sun has plasma. This sun is made up of gases, H2 and primarily H2 and He, but they H2 exists as plasma in the case of sun. Okay, and BEC, they exist at very low temperatures. Then you also have a fermionic state of matter. This is a new state of matter that people have discovered. Fermionic state of matter. Research is underway on this. This also exists at very low temperatures. Okay, so these are the three states of matter. One is under research, two are well established. Now solid, liquid and gas, these are the states of matter that we encounter in our everyday lives. So you can see a solid state of matter, so these can be considered as individual atoms of molecules. It is more closely packed. Closely packed as in a given volume, let's say this is your cube. Okay, you will find more molecules or atoms. Okay, let's say number of molecules here is n1, let's take the similar size of cube here. Okay, you can see the cube, let's say the number of particles is n2, and in the case of gas, let's take this cube. Okay, so let's say here it is n3. Okay, so you can see in the case of a solid, n1 is high. So if every particle, atom, or so in this case atom or molecule has a given fixed mass m, okay, so m, so here total mass will be n1m, m total mass is n1 into m. In the case of liquid, it will be, let's say m2, or we can take m total, let's take m2, or here we can just write m total, it will be n2 into m. In the case of gas, it will be m total equal to m3 into, sorry, n3 into m. Okay, and n1, as you can see from visually, your n1 is greater than n2 is greater than n3. Okay, so that means more mass is packed in a fixed space in the case of solid. Generally there are exceptions also, we will talk about these exceptions after this. Then your liquid phase, then your gaseous phase. Okay, so that means your density increases. Your density is amount of mass packed in given unit volume. Okay, so it will be m by v, mass by volume. So for a given volume, generally solids will have more mass than liquids than gases. Okay, so basically it will be more dense. So if you are taking, let's say, this pen, so a pen is made of solid, so in this case it is made up of solid phase, so it is more you will find it to be more heavy because it is more dense. Let's say this pen was made up of liquid, let's say it was enclosed in a plastic casing, so then in that case the liquid will be of, for the same volume, it will be lighter generally. Let's say it is again a transparent container in which you put some gas in. Now again for the same volume, the mass of this pen will be lower in the case of gas. Okay. Now there are exceptions. What exception? Last class I had told that when you go to in our solar system, okay, if this is our solar system, I'll clear the board. Okay, so I had told in our solar system, so if you go to the extreme out of the orbit of Pluto, there is something called so out of the orbit of Pluto you find lots of comets, asteroids, protoplanets. Okay, so what happens is, I had told there you find a rare type of ice which is very dense. Generally ice has a structure, cage like structure, so it will be like this: H O H H H O H O H, then here O H. So you can see it is a cage like structure. These are called, the dotted lines are the covalent bonds. Okay, covalent bonds I think you will learn in the coming classes. Covalent bond is basically a chemical bond in which one electron is shared by two neighboring atoms. So here hydrogen and oxygen are there, they are sharing one electron each. One electron is coming from hydrogen, one electron is coming from oxygen, and then they are forming a covalent bond. Then these dotted lines, they are called hydrogen bonds. This one you won't learn in this class, you will probably learn in 11th grade. Just remember, oxygen and hydrogen in water, apart from forming a covalent bond, they also form something called a hydrogen bond. Okay, this bond is weaker than the covalent bond, but it is necessary for liquid water or solid ice to exist. You can see there are some vacant spaces, okay, in the structure, vacant spaces, okay. Sometimes molecules of sufficient size, so smaller size basically, like H2 is a small molecule, they can exist in these vacant spaces. Okay, even if they don't exist, if your structure is hollow like a ship, so a ship is made up of metal. Okay, ship is generally made of steel. Okay, we know steel is more dense than water. We know a substance, if it is more dense than water, it will sink. Okay, but in the case of ship, it does not sink. Why? Because ships are made of hollow spaces. So hollow spaces reduces the density of the ship, even though it is made up of metal. That way it is less dense than water, and that thus it can float on water, even though it is made up of metal. Similarly, in the case of ice, normal ice which we find in our freezer or we use in our everyday lives, it has air contained in it, or sometimes if air is not in those vacant spaces, it has vacant spaces in them, hollow spaces. Because of this hollow spaces, the density of ice reduces. Density reduces. Because of less density, ice floats on water. Okay, ice will float on water. That is why on our polar ice caps, Arctic and Antarctic, you have ice sheets which are floating on water. Okay, in the case of Antarctic, there is a continent there, there is solid ground there, but in the case of Arctic, I think there is no solid ground, and less solid ground, like it's not a continent, you basically have the tips of various continents. So you have on one side you have Canada, I think other side you have Russia, and you have the Scandinavian islands, I think you have your Norway, exactly which country I don't remember, but the Scandinavian countries, and you have Greenland there. So the tips are covered by various countries and continents. Okay, and in the middle there is the ocean, that's the Arctic Ocean, and Arctic Ocean has ice sheets. Okay, big ice sheets. You might have heard 10-kilometer long ice sheets, 50-kilometer long ice sheets. So they are big, but they float on water because they are less dense than water. Okay. Now this type of ice is called ice 1. Okay, ice has various types depending on the pressure and temperature under which it was formed. It has various types. Okay, so last class I had told some forms of ice are more dense than water. One of them is called ice 7. Okay, it is found in these comets, not exactly the comets. For that you actually require a lot of pressure, 3 to 5 gigapascals pressure, 3 to 5 gigapascal pressure. Pascal is a unit of pressure. So you will probably learn this year in physics, pressure is force by area, P equal to F by A. Okay, and we know F equal to mass into acceleration. This again you will learn in this grade. So just remember our normal atmospheric pressure, the pressure which you are experiencing right now, normal pressure is about 10 to the power 5 pascals. Okay, but the pressure required to form ice 7, ice 7 is a form of ice. Because of extreme pressure, it is more dense than water, the structure changes, it is not the cage like structure of ice 1. So what will happen is, so you can see 3 to 5 gigapascal is 3, let's say minimal value will take 3 into 10 to the power 9 pascals. So it is about 10,000, I think 30,000 times greater pressure you will form this. This happens on the outer reaches of our solar system when two comets collide. So comets are icy objects, when they collide they form ice 7. Or if you go to moons, like, so our solar system has lots of moons, we have lots of 8 planets, but we also have lots of moons. So on in the planet of Europa, or you can find icy moons, any moon that is icy, basically it's a frozen world, lot of water is there, but since it is so far away from the sun, it is frozen, you can find this ice 7. Okay, on earth also we find ice 7. Scientists, when they dig, when they are digging inside earth, they find diamonds. Okay, diamonds are found generally under the ground. So those diamonds, some of these diamonds, they are formed at a depth of 610 kilometers. So 610 kilometers below the earth's surface. At that point you reach the mantle. Okay, so we have the crust, we have the core, with the mantle we have the crust. Crust is on which we are living, mantle is the layer below the crust. So at 610 kilometers the pressure and temperature is extremely high. So when these diamonds form, they trap ice in the center of them. That ice is also ice 7. Okay, so ice 7 is more dense than water, it will sink in water. If you put it in water, it will sink in water. Another interesting property of ice 7 is it can exist at very high temperatures. It can exist at 100 degrees Celsius. Normal ice will turn to water and turn to steam, but ice 7 can exist at 100 degrees Celsius also. Okay, if you have sufficient pressure, 3 to 5 gigapascal. So this again is a property of materials. This you will learn in higher grades, something called phase diagram. Okay. So these are all experimentally proved science. This has been proven. Okay. Then you can see liquid water. The density is somewhere in between. If you take I7, then it is more dense than water. Then this structure and this theory, this maths that I did, n1 into m, n2 into m, n3 into m, that will be valid. Okay, generally there will be exceptions also. So if you go for a generic trend, like in this case I am taking I7, that will be more dense than liquid water, that will be more dense than your steam. Okay, and other properties also exist. I had told last class, I think. You've got rigidity, you've got fixed shape, fixed volume, so all these also come along. We'll go to the next slide. After a long research, it was concluded that matter has particulate nature. So it took a lot of time actually to realize that matter is not continuous. Continuous means like this bark of a tree, it is a single piece. Okay, it is a single piece, but it is not. It is made up of various atoms and molecules. You will find here carbon, you will find here hydrogen, you will find here oxygen. Okay, you will find here, I think, even, so you will find lot of atoms, lot of molecules that make up this bark of tree, and because they have aggregated together in a structure that is visible to our eye. We cannot see atoms because atoms are really small. They are of the order of 10 to the power minus 10 meters. Okay, or that is like really small. We can't see. Our eyes are not that sharp. So we only see the bulk phase of matter. Bulk phase means, you know, the aggregate phase, where all these atoms and the molecules involved, they have aggregated together to form a big piece. Okay. So this is a easy question. The question is, select the model that represents as an example of the particulate nature of matter. So basically here we have one side sand. Okay, we have sand, and in one side we have wood. So you need to find a model. Okay, sand is also not exactly a particulate nature of matter, because individual sand grains exist. Okay, sand is made up of silicon compounds, Si compounds. Okay, so but which can be used to demonstrate as a model, like as an example. So you can take sand, right? Sand has sand grains. So these sand grains, when they are aggregated together, they form a heap. That heap is visible to you. Or you might have seen something called beach sand art. Okay, sand art also exists. So sand art is, you could have seen, there is a famous sand artist. His name is Sudarshan. Okay, you can see he makes really beautiful pieces of sand art, sand sculptures on important events like Olympics or Commonwealth Games or New Year or any major festival, Diwali, Holi. So you can see he is aggregating individual sand particles to create the macro sculpture, which is visible to you. Individual sand particle may or may not be visible to you, but the macro is visible. So the same thing happens in the case of everything, every piece of matter. Atoms and molecules, they aggregate together to form a bulk visible phase, not phase, bulk visible structure, which is visible to us, which we can interact and use it. We can't interact with individual atoms, but we can interact with the aggregate of them, like this pen for example. So obviously the answer will be sand. Now wood you can't take, because wood is a single block. So I cannot take a big block and tell it to be an example, a model for particulate nature of matter. Although wood is also made up of particles of matter, and sand is also made up of particles of matter, but here we are saying for case for model. Okay. So we will go to the next slide. So again, this is a connect the bubble question. It's an easy question. Question is, connect the bubbles to match the nature of matter which was concluded after a long research. So nature of matter, as we have told, is particulate. Okay, It is not made up of continuous phase or both particulate and continuous. It has no continuity. It is made up of particles. Okay. So correct option will be, match will be this. So how few drops of potassium permanganate turn a good amount of water into a pink color? Okay. So potassium permanganate is made up of KMnO4. Okay. So if you put it in water, okay, it will turn to K plus and MnO4 minus ions. Okay. Now this process is called dissolution. Exact word is hydration. Hydration is the process by which you dissolve any substance in water. Okay. So what happens is K plus, it gets surrounded by water molecules. Okay. It gets surrounded by water molecules. Now water molecules, I think I have told in the last class, they are polar compounds. Polarity means one of the atoms in water molecule attracts the shared pair of electron towards itself. Okay, I had told this is a covalent bond. Okay, covalent bond. There is a property called electronegativity by which an atom attracts the shared pair of electron towards itself and thus develops polarity in the compound. Okay. So what happens? Water, oxygen is the electronegative element, so it will attract the shared pair of electrons towards itself. Okay. And it will develop a partial negative charge, and hydrogen, thus since the shared electrons are moving away from it, it develops a partial positive charge. Okay. So negative charge, here also it will be delta negative. Delta is a symbol for partial charges. This will be delta plus, this will be delta plus. So what they will do is they will surround the potassium ion. Potassium is K plus. So the negative part of water molecule, which is the oxygen part, it will surround the K plus, and MnO4 minus. Okay, MnO4 minus will also be surrounded by, the positive part of water molecules. Okay, so these will have delta positive, the hydrogen, so they will surround the water molecule. Okay, so by this way they cause dissolution or hydration. Now color comes because in the structure of KMnO4, MnO4 minus is something like this structure. Okay, this is MnO4 minus ion, permanganate ion. So what happens? It has a electron cell bond. Because of the electronic transitions, they emit a purple light. Okay, purple light that is caught by our eyes, and we perceive it to be purple. Okay. Now in the solution phase, when you dissolve KMnO4 in water, KMnO4 is soluble in water, so it will just spread out. Okay, it will spread out throughout the volume of water and give it a purple tinge. So if this is a beaker and you have put some KMnO4 in it, so it will just spread out. If you stir it, you can make this spreading happen faster, and this will give you purple color. So this is also proof that matter has particulate nature. If it was continuous, so KMnO4 would have formed a blob, a purple blob, but that is not the case. The entire water changes to purple. This shows that the particles of KMnO4, K plus and MnO4 minus, they spread out throughout the entire volume and they give purple color. Okay. We go to the next slide. Here model again they are using sand. Is nature of matter continuous or particulate? So we have proved in the case of KMnO4 also we used that matter is particulate in nature, it is not continuous. Even this wood, if you take it to a grind it, you will get sawdust. Okay, even this continuous phase of wood or plywood, it is also grindable. Okay, so it gives you sawdust. Now that sawdust even is formed of other atoms, carbon, hydrogen, oxygen. Okay, they combine to form that sawdust. Okay, so this also shows matter is particulate. Go to the next slide. The sugar crystals disappeared and there was no change in the level of water during dissolution of sugar. Okay, so what happens is sugar crystals, sugar is soluble in water. So what happens? Water breaks the bonds between the sugar molecules. Sugar is sucrose, okay. Sugar is sucrose, okay. Sugar is sucrose. So what water does it? Water breaks down, you know, this sugar cube. There are some you know, attractive forces between individual sugar molecules, okay. So sucrose molecules basically. So water breaks down those individual attractive forces, okay. It breaks down, and what it does, it sugar molecules, individual sugar molecules, they are sort of, you know, they go into the spaces between water, and thus they are dissolved in it, okay. So that is why it is dissolving in water, and the volume thus does not increase. Sugar cubes also have a volume, so there is no change in volume, okay. So you can see here, when you are dissolving, water molecules are there, these sugar basically individual sugar molecules, they go between the spaces of water molecules. Basically water molecules have, the bonds between water molecule and sugar is better than individual sugar molecules, so they break the bonds that sugar molecules have between them in the sugar cube, okay. Not exactly better, better would be the not the correct term. Just remember, they break the bonds between individual sugar molecules in the sugar cube, and those individual sucrose molecules, correct exact term would be sucrose, those sucrose molecules go between the spaces of water and that, okay. Now interaction between water and sucrose, I will tell you in the next class. For now just remember, there is a they go between the spaces, okay. So this again shows that matter is particulate in nature. If sugar, if it was continuous, you would get a big blob of sugar, okay, but you don't get that. We get individual sucrose molecules, so that shows matter is particulate in nature. So this question is, what happens to sugar particles when sugar is dissolved in water? Because they are getting in between the spaces, sugar also, when you are dissolving sugar, it does not increase the water level, it stays constant, okay. What happens to sugar particles when sugar is dissolved in water? The particles of sugar occupy the spaces between the particles of water. So this is correct. Sugar does not dissolve in water. This is wrong. We know sugar can be mixed in water. Third option is the particles of sugar dissolve and raise the level of water. This is also wrong. This question is easy. Connect the bubbles to describe the nature of matter. We know nature of matter is particulate, not continuous. Okay. Why does lemon juice served in different glasses taste the same? So the thing is, we know last year I think you have read that some solutions are homogeneous, okay. Homogeneous means the composition of solution is same. In this case, one of the solution part is your what, lemon juice, okay. Lemon juice is the liquid, so it is a liquid solution. So lemon juice is a liquid which is dissolved in water, okay. Then you add some salt or sugar depending on your taste. So what happens is, if you take a beaker, okay, and if you add 10 ml of lemon juice per 100 ml of water, so your mass volume of, okay, so 10 ml of lemon juice per 100 ml of water, okay, or let's, okay, then when you are adding it, okay, so if you are adding 10 ml of lemon juice per 100 ml of water, and let's say 100 ml of, let's say you have, okay, let's take it to variables, okay. So let's say you have a ml of lemon juice, a ml of lemon juice per b ml of solution, in this case lime water, not lime water, lemon juice, okay. So what you do is b ml of lemon juice, so if you take, so there b ml of lemon juice solution, okay, so if there is b ml of solution, a and b are variables, okay. I think you know what is a variable, x and y, a and b, x, y, z, okay. So if you take a syringe, so let's take, you take a syringe, there is a hole in this container, and you take out some part of the lemon juice, okay, and then you try to find out the concentration. So you will find that even in this small syringe, the concentration of lemon juice is a ml of lemon juice in b ml of water, b ml of solution. So the concentration always stays same, and depending on concentration, the amount of particles of lemon juice. So lemon juice is again made up of lots of stuff. One of them is citric acid because it is a citric fruit. So the amount of particles in the lemon juice per volume of given volume of solution, that is responsible for taste. Okay, so you have taste buds in your tongue, so they are responsible for taste. So they can detect that if more or less lemon juice particles are present, it will be more or less sour. Okay, so because the solution is homogeneous, the composition of solution remains the same throughout. Even if you take a syringe, or if you take a dropper, or if you take a big bucket, the taste will stay same. The reason is concentration per unit volume lemon juice per unit volume of solution will be same in all the cases. Okay, so here also again you can see that matter is particulate, because if it was continuous, lemon juice, this solution might have tasted different in when you take samples from different areas of the beaker. Okay, so if you are taking a sample from this area, let us say it is x, and if you are taking a sample from this area, let us say it is y, the taste of lemon juice in x and y would have been different. But since matter is particulate and the solution is homogeneous, it will stay, the taste will stay same throughout. Okay, so we will go to the next slide. So this is again experiment. Okay, so what is done here is 2 gram of copper sulphate is dissolved in 100 ml of water. Okay, initially, so copper sulphate solution is called blue vitriol, copper sulphate is CuSO4. So what you do is, you take a dropper, this is called a dropper, you take 10 ml of the previous solution and add it to 90 ml of water. Okay, so again volume will be 100 ml, again you take 10 ml, you add to 90 ml of water, and copper sulphate is soluble in water. So in this case the volume is not increasing. Okay, 10 ml of previous solution. So you can see the color is changing depending, it's getting fader and fader, it is fading as we go right. The reason is, okay, so there is a reason for it. So initially there was 2 gram of copper sulphate. Okay, so initially there was 2 gram of copper sulphate in 100 ml of water. Again this is a homogeneous solution, the concentration will stay same. So if there is 2 gram of copper sulphate in 100 ml of water, when you are taking a dropper and taking 10 ml from it, what will happen? So in 100 ml 2 gram of copper sulphate is there, so in 10 ml 0.2 gram will stay, 0.2 gram, because this 2 gram per 100 ml, this concentration you have to maintain throughout. Okay, so because it is a homogeneous solution, even in 10 gram, to make 2 gram per 100 ml, so if you take 0.2 and if you take 0.1, because sorry 0.2 by 10 ml, okay, so the concentration will be still same. So if the concentration is same, that means if I am taking 100 gram, I am getting 2 gram copper sulphate. If I take 10 ml of water, solution, I will get 0.2 gram of copper sulphate. Now again this 0.2 gram is in 100 ml of water. Okay, 100 ml of water, 100 ml of water. Okay, so again 0.2 gram is in 100 ml of water. Again 10 ml of this you are putting in the third beaker. So again this will reduce the amount of copper sulphate present in that solution sample that you are taking. It will be 0.02, because again to maintain that concentration, so new concentration is 0.2 gram per 100 ml. So to maintain that, if you are taking 10 ml, it has to be 0.02 gram of copper sulphate. So again now it is 100 ml. Again from here you are taking 10 ml of the solution, so it will be 0.002 per 100 ml. Again from here you are taking 10 ml, so it will be 0.0002 gram per 100 ml of solution. Okay, so you can see the concentration of copper sulphate, CuSO4, copper sulphate, is reducing by factor of 10 in every iteration. every time you are using the dropper, it is reducing by the factor of 10, and thus I had told you, because of the electronic transitions present in the copper sulfate, whatever is there, you get color. Okay, so because of that, as the number of copper sulfate particles, copper sulfate is not, you cannot say copper sulfate as a single entity, they exist in aqueous form. Okay, so whatever aqueous form they exist, they are reducing, okay, by a factor of 10 in every iteration. So because the number is reducing, the color is also reducing, because the more the number, more the electronic interactions, and thus more is the color. As there are less electronic interaction, less is the color. So that is why in the most faint one, the concentration of copper sulfate is the least. In the most, you know, darker one, the concentration of copper sulfate is the highest. This we also experience in our everyday life. So again, in that lime juice, if you add more salt, it will be salty. If you add less salt, it will be less salty. Reason is the number of particles are directly dependent, the saltiness of the lime juice is directly dependent on number of particles. So it is reducing as you are adding less and less salt. Okay, this is a visual cue. The example I gave you is a taste cue. Okay, so we'll go to the next slide. So copper sulfate, this experiment you might have done, purification of matter, crystallization of copper sulfate. So conclusions from the experiment: number of copper sulfate particles in initial sample were in millions. Number of these particles, okay, not exactly in millions. I can give you the exact number. Okay, it's not in millions. This is a bit wrong. You can say it to be millions, but exactly what happens is it will be copper sulfate. I think it will be approximately 63.5 plus sulfate, I think 32 plus O4. O4 is, so anyway, you can say it to be in millions, so it is not wrong. Okay, you can say it to be millions, but number of these particles which, so when you are reducing the concentration of any substance in a solution, you undergo a process called dilution. Okay, so the color is fading because the number of particles are keeping on reducing. Okay, particles that are constituents of matter are much smaller than we can see on naked. So I had told you order is about 10 to the power minus 10 meter to 10 to the power minus 12 meters. So this is very small, we can't see. Our eyes can barely see something which is a 1 millimeter. 1 mm is 10 to the power minus 3 meter. So these things are a million times smaller than what we can generally see, even after a lot of effort. To see an object of 1 mm, you have to be close enough so you can see it. Okay, even then if you have some eye defect, you might not even see it without the use of some specs or contact lens. Okay, so we'll go to the next slide. Question is, which of the following samples contain the minimum number of copper sulfate particles? So we had solved this. So I had told you that as the number of particles reduces, the color reduces because of less electronic transitions. Thus, this will be your answer. Okay. How do particles of copper sulfate dissolve in water? So I had explained this actually. So how KMnO4 I had explained that the water surrounds, you know, so water has a negative part, positive part, because it is a polar compound. So thus it surrounds CO2 plus. So the negative part, it will surround the CO2 plus. So it will surround it. So it will stabilize it. Similarly, the positive part, copper is the positive part, sulfate ion SO4 2 minus is the negative part. So water will again surround it. So in this case, the positive end of water will surround. Okay, so it will be HOH, delta positive, delta negative, again HOHO, delta positive, delta negative. So it surrounds it. Okay, this is how something is dissolved in water. This process is called hydration. Okay, so we'll go to the next slide. So guys, please visit our platform imbibe.com. Okay, so there you can just sign up and log in, and go to select your grade 9 CBSE, go to the books. We have NCERT book, exemplar book, and apart from that lots of reference books, so you can go there and solve. Okay, it's very handy. Next is this our QR code. We have a Telegram channel, so you can join the Telegram channel by scanning the QR code. Please also subscribe and switch on the bell notification icon in your YouTube, so you can get notifications, and please like the video if you like it, so that this video gets more traction, and we can continue giving good content. So thank you guys for attending today's class.
Keep imbibing. We believe in you.